Hello, all you calculus students out there. Earlier this week, I was asked by one of my kids to go over Riemann sums and make sure that they had a good understanding of the basics of Riemann sums. So this was a real quick review on Riemann sums, but we're also going to touch upon under and over approximations as well in a couple of different contexts. So here we go. A Riemann sum, very basic. How do we approximate an integral? Riemann sums approximate integrals. That's what we need to know. Now, sometimes we get confused and we say Riemann sums approximate areas. Well, that's only true if the integral is being used to find an area. Remember, integrals can add up anything at all. They don't have to add up areas. So I would much rather say that a Riemann sum approximates an integral, and whatever that integral is being used for, the Riemann sum will also be approximating that. So to get an idea of how Riemann sums work, we have a function here on the screen, and we would like to find the area of this function. Using typical geometry, we are limited to only being able to find the area of shapes that we know. This is not a specific shape we know. It's not a rectangle, it's not a triangle, it's not a semicircle, it's nothing like that. So our geometry ways are out. So the whole idea behind Riemann sums is to take advantage of the fact that we already do know some shapes like rectangles and triangles, and let's try to use those to figure out this. So what would happen if I took and I divided this section up like this? And now I've got a bunch of strips. Here's what I could do. I could now attempt to find an approximation for this problem by drawing a bunch of different rectangles. Now, again, I'm just kind of arbitrarily picking where the rectangles go in this one, but what's nice about it is in order to find the area of a rectangle, all we need to know is its base times its height. Now, in this drawing, we can use the function that we're given, along with the Cartesian coordinate system, to actually compute the bases and the heights, and therefore, we're going to be able to get an area approximation for this. Now, in this case, the area we would be finding would include some parts that are outside the area, but we'd also be missing some parts that are inside, so we're hoping that those are going to get balanced out. But the thing about Riemann sums is if you do it in a systematic way, in an orderly way, you can actually use it to find a pretty good approximation. In this situation, I've done it so that all the rectangles are inside the shape that we're looking for. So we would know that whatever answer we got by adding up these rectangles would be an under approximation. But again, the idea is, can we use the example to find this base and this height right here? And again, as long as we know this function, all of these heights are just going to be y values along the function. So all we're going to have to do is plug into the function to find those heights, because this point right here is an input-output, an xy, and if we're given the function, we'll be able to find that point. And really, that point is the key to finding both the base and the height in this situation. So we're going to look at a couple of examples that we might see on an AP exam and how we answer them. But again, the idea is in Riemann sums, we're going to use shapes that we already know. And I should say this, there are 4 types of Riemann sums that we need for the AP exam. Those 4 types of Riemann sums are called a left-hand approximation, a right approximation, or a right-hand approximation as I often call it. We're going to use a trapezoidal approximation. And we're also going to use a midpoint approximation. Now, what's nice about the left and the right and the midpoint is they all use rectangles. So it's all about finding bases and heights for both of those, or all 3 of those. And then for the trapezoidal rule, kind of simple, we're going to be using the trapezoid. So just a real quick reminder, the area of a trapezoid is the average of the 2 bases times the height of the trapezoid. So knowing these geometric area formulas, we're ready to take a peek at how to handle the Riemann sum. So very often on the AP exam, the way a Riemann sum problem is given is they give you a table of data. Now, this is nice because they're giving us all the values we need. We're not going to have to compute too much. But what's unfortunate about this is we have no real information about what's happening in between points. So what I mean by that is I know I've got an x value of 1 here and a y value of 4. And then the next point I see is 3 comma 10. But I don't have a ton of information about what's happening between 1 and 3, at least not from the table itself. So that's the downside of this. Again, plus is that all the values are given to us. The downside, no knowledge of what's happening in between our points. So in this particular example, we're asked to use a left Riemann sum. And the idea here is that we're going to take this shape, and I'm just going to draw a picture to start. And it's going to go from an x value of 1 to an x value of 10. And then we're just going to have some y values above it. So this one's going to be up 1. The next one is going to be at the value 3, and it's going to go up 3. I'm sorry, the value at 1 is 4. Okay, the y value at 3 is 10. The y value at 7 is 14. The y value at 9 is 16. And the y value at 10 is 17. So what we do is we have a tendency to want to connect these ends of these heights, but again, we really don't have a lot of information about what's happening from between 1 and 3, 3 and 7, 7 and 9, 9 and 10 from the table itself. But this is what I do know, that I have 3 sides of my triangle pretty much outlined. And again, what I mean by that is if we think about this from here to here, from 1 to 3, those are the 3 sides of our rectangle. We're being asked to complete the rectangle using a left-hand Riemann sum. So what that means is I have to choose between the heights of 4 and 10. They're telling me to use a left-hand Riemann sum. The choice is made for me. I'm going to use a height of 4. So this rectangle right here is going to have a base of 2 and a height of 4. In my next region, I'm now going between 3 and 7. My 2 choices are 10 or 14. They're telling me use the left, so I'm going to use 10 for this one. In the next rectangle, I'm between 7 and 9. My 2 choices are 14 and 16, but because they told me to use the left hand, I'm using 14. And the last region between 9 and 10, my 2 choices for heights are 16 and 17. They told me to go left, so I'm going to use 16. So from here, I can now find the base and the height for each one of these rectangles. The base for rectangle number 1 goes from 1 to 3, so my base is 2. For the next rectangle, I'm going between 3 and 7, so my base is 4. In my next rectangle, I'm going 7 to 9, base of 2. And in my last rectangle, I've got a base of 1. So the way I'd like to write this answer, I'm going to say that I am approximating the integral from 1 to 10 of f of x dx. And that will be approximately equal to the sum of the areas of these 4 rectangles. So I always like to do base times height and do a little skeleton first. And give myself some room here. And just add in that last base times height. And now the bases, I always do the bases first. I'm going to go through and enter all the bases. The base of my first rectangle is 2. The base of my second rectangle is 4. The base of my third rectangle is 2. And the base of my last rectangle is 1. Now I want to go back and use the appropriate heights. The heights were on the left-hand side in each case. So my first height is 4. My second height is 10. My third height is 14. And my fourth height is 16. Notice in this particular example, the height 17 does not get used because we're choosing to do a left-hand approximation. So as far as the AP exam is concerned, this is a perfectly acceptable final answer. You do not have to simplify any of your arithmetic on the AP exam. Of course, if you wanted to, you could go through and say that this is going to be 8 plus 40 plus 28 plus 16. And that's going to get us a total of 48, 58, 68, 76, 86, 92, I believe. Okay, 68, 78. Yeah, 92. But again, I'm just leaving it in the expanded form. And this is the idea behind a Riemann sum, okay? You just make a bunch of rectangles, you find the bases, you find the heights. Now, that being said, you do not have to get into this situation where you're drawing this every single time. This is just my way of summarizing what was kind of in the table already. So I'm just leaving that there to show you for an introduction how to set up the Riemann sum. Okay. So in the next example, we are now asked to find from least to greatest the left Riemann sum, the right, the trapezoidal, and then the exact value, and put these in order from the least to the greatest. So in this case, we're going to go through, we're going to do kind of the same calculations. We just found our answer for the left-hand Riemann sum. That final answer we got a minute ago was 92. So I already know that my left-hand Riemann sum is 92. Let's take a look at what the right-hand Riemann sum would be. In order to find that right-hand Riemann sum, again, we're going to use 4 rectangles. And in the right-hand Riemann sum, again, our base from 1 to 3 is still a base of 2. From 3 to 7, we have a base of 4. From 7 to 9, we've got a base of 2. And from 9 to 10, we've got a base of 1. So now we're looking at the right-hand approximation. So in rectangle number 1, we're choosing between 4 and 10, but we're going to choose the height that is on the right. So this time we choose 10. In rectangle number 2, we're choosing between the heights 10 and 14, but because we're doing a right-hand approximation, we'll choose 14. In rectangle number 3, we're choosing between the heights 14 and 16. Right one is going to be 16. And in rectangle number 4, we're choosing between 16 and 17. So we're going to be choosing 17. So that will get us our right-hand approximation. That's going to be equal to 20 plus 4 times 14 is 56, plus 2 times 16 is 32, plus 1 times 17 is 17. So our answer here is going to be 76, 108, 125. So we know that the right-hand Riemann sum has a value of 125. Doing the trapezoidal sum, we're going to go and do the average of the bases times the height for this one. So I'm going to set up 4 templates for trapezoids. Average of the bases times the height in each one. But in this particular example, what you have to realize, and I'm just going to draw one real quick trapezoid here, the one that starts at 1 and ends at 3. We've got a function value going up a height of 4, and then we've got a function value going up a height of 10. The way we're going to make our trapezoid is we are going to connect them like this. So this will be the area that we're talking about from 1 to 3. So in this case, the heights of the trapezoid are the parallel sides. So 4 and 10 will be our heights. So I'll put 4 here and 10 here, and then 4 and 10 will be our bases. I apologize. 4 and 10 will be our bases. The height will be the distance between the parallel sides. So the height will be the distance from 1 to 3, which will be 2. And that's what we're going to get for our trapezoidal rule for the first interval. In the next interval, our 2 bases will be 10 and 14. And our height this time will be from 3 to 7, and there's that 4 value. The next one, our bases will be from 14 to 16. And our height will be from 7 to 9, which will be 2. And then our last one, our bases will be from 16 to 17. And our height will be 1. Okay, so that will be our trapezoidal approximation. If we compute all of this, we're going to end up with, let's see here, 115, 102, 115, 102, 217 divided by 2, which is 108 and 1/2. Okay, 108 and 1/2. So that'll be the trapezoidal, 108 and 1/2. So now we know the left Riemann sum is 92. We know the right Riemann sum is 125. We know the trapezoidal sum is 108 and 1/2. How do we do the exact value on this one? And that seems like it's going to be pretty much impossible to do because, again, we only have the values at 1, 3, 7, 9, and 10. We don't have any other information. But here's the thing you have to understand. I don't need to know the exact value. I just need to know where it compares to all my other approximations. So what we need to do now is we need to go back a little bit and we need to read this question a little more closely, because back in the beginning, I told you guys that, hey, we only have information in the table and that doesn't give us the exact information. But if we read the stem of this question, we've got a little more information, specifically right here. We're told that f prime of x is positive and f prime of x is decreasing. Well, if f prime of x is positive, that's just another way of saying our function is increasing. And if we're told that f prime of x is decreasing, that's just another way of saying our function is concave down. So that's not just the table anymore. Now we've got some more information. And this is the key to understanding over and under approximations. Over and under approximations with Riemann sums are all about knowing whether or not your function is increasing and decreasing, or whether it's concave up or concave down. And we're going to take a look at that right now. So in this example, we are told that our function is increasing concave down. Let's just draw a picture of that real quick, okay? So if I draw any function with the properties that it's increasing concave down, we're going to get this kind of shape right here. Now, if I go to do a Riemann sum on this, and I start dividing this up into regions, okay? So we're going to start cutting this into those strips, which are going to become our rectangles and our trapezoids, okay? It is pretty clear if we're increasing, a left-hand Riemann sum is being taken from the lowest height in the interval. So if we are increasing, the left-hand Riemann sum is always going to be an under approximate. Okay, if we're increasing, it's got to be that way, because in every interval, we're choosing the lowest possible y value. So all the other y values are above our choice for the height. If we go now and we look at the trapezoidal rule, well, the trapezoidal rule says to connect the two spots like this and the two spots like this. So now, what do we know about the trapezoidal rule in this case? Well, again, it's an under approximation. But is it an under because we're increasing? Not so fast, because I could draw another function here that is also increasing. But if I go to do a trapezoidal rule on this particular function, I am going to have an over approximation this time. So what dictates whether or not a trapezoidal rule approximation is under or over? It's not increasing or decreasing at all. It's actually the concavity of the shape. We're going to have a trapezoidal rule that's an under approximation if we have a function that is concave down. That will make the trapezoidal rule an under approximation. So in our example, we were given that we had an increasing function and a concave down function. So our trapezoidal rule is going to be an under approximation. But take a look at the picture and notice this as well. It's an under approximation, but it is greater than our left-hand approximation. So now we know our left hand's less than our trapezoidal. Last one we're going to do is we're going to look at the right-hand approximation. And if we go a right-hand approximation on this, that actually means in that region we're going from the right side. So in this case, that would be the right-hand approximation. And this would be the right-hand approximation. So now we know our right-hand Riemann sum is an over approximation. And again, this is because we are using an increasing function. So where does that leave the actual answer? Well, from this drawing, what we can tell, pretty quickly, let's move this out of the way. we can see that the greatest value is going to be the trapezoidal approximation. I'm sorry, not the trapezoidal, the right-hand approximation, the right-hand Riemann sum. Then the next value that would come next is going to be the actual value, because that's the exact thing. Then our biggest under approximation, which is our trapezoidal rule, our trapezoidal Riemann sum. And then last but not least is going to be our left-hand Riemann sum. So back here, when we calculated this, we got the right Riemann sum was 125. We've got the trapezoidal rule was 108.5. We found the left-hand Riemann sum to be 92. And to be honest, we still don't know the actual value, but it doesn't matter. The problem didn't ask for the actual value. It just asked which one, what was the order from greatest to least. In this case, is how I'm ordering them. So we never actually have to find the actual value. And one more thing, to be honest with you, we don't even have to find any of these approximations. Just by knowing the shape of the graph, we could have answered this question. Okay, so what I want to do real quickly is I want to come back up here and I just want to summarize this. If we are using a right-hand approximation, a right-hand Riemann sum, and we know that the function is increasing versus the function is decreasing, and then same thing for a left-hand Riemann sum. Well, if you're doing a right-hand sum and the function is increasing, just think about that. Here's the drawing. If I do a right-hand sum, I'm going to have an over approximation. If the function is decreasing and I do a right-hand sum, then I'm going to have an under approximation. If I'm doing a left hand, we're going to get the exact reverse of that. So if the function's increasing and it's a left hand, we're going to have an under approximation, and it's going to be an over approximation if the function is decreasing. Now for the trapezoidal rule, it's not about increasing or decreasing. It's about your function being concave down or your function being concave up. And again, if your function is concave down and you're doing a trapezoidal rule, you are going to have an under approximation. And if your function is concave up and you're doing a trapezoidal rule, you're going to have an over approximation. So increasing and decreasing really don't make that much of a difference for the trapezoidal rule. Okay, so that's how you're going to be able to tell whether or not you've got an over and under approximation for these guys. There is a fourth Riemann sum called the midpoint rule, or the midpoint Riemann sum, and that would mean you're going to actually find the height from a midpoint. So in other words, if you were given an interval, let's say from 0 to 8, and you were asked to do 2 rectangles, okay, normally we would find the heights either at the ends. 0 and 4 would be our choices. If you're doing a midpoint approximation, the place you're going to get your height is actually going to be right here at 2, and then you're going to find your height again at 6. So you're actually going to use the midpoint x values to find your heights. Over and under approximations become much more challenging. With the midpoint, we need a lot more extra information. So it's typically not asked on the AP exam. So we're not going to discuss it here on this particular session. The next question I want to answer is find the right-hand Riemann sum, but this time pay attention. This is actually saying for f prime of x. So the right-hand Riemann sum for f prime of x, again, we've got the information in the table, but we just got to look at the right ones. We're going to keep our x values, but we're going to be using f prime of x this time. So again, we're going to do right-hand Riemann sum. We're going to have 4 rectangles. So base times height plus base times height plus base times height plus base times height. And now we're going to go through and I'm going to do the base is going to be from 1 to 3. So that's 2. The next base is 4 from 3 to 7. Next one from 7 to 9 is 2. And next one from 9 to 10 is 1. And now I've got to choose the correct height, and it's going to be the right one. But remember, we're using F prime. So I'm choosing between these two, and the right hand is going to be 7/2. And the next one, we're choosing between 7/2 and 13/4. So the right one's going to be 13/4. And the next one, we're choosing between 13/4 and 13/5, but the right one's going to be 13/5. And in the last one, we're choosing between 13/5 and 1. So the right one is going to be 1. So again, we are perfectly good leaving this as our final answer, okay? But now, is this an under approximation or an over approximation? Well, you've got to remember, in the given information, it told us that f prime of x was decreasing. So since f prime of x is decreasing, we've got a drawing that's going like this. We're doing our shapes. We're choosing the right-hand side. And as a right-hand Riemann sum on a decreasing shape, this is going to be an under approximation. So this is an under approximation because f prime of x is decreasing on the interval from x is between 1 and 10. And we are using a right-hand approximation. That justification will give us full credit. That answer will give us full credit. We are good to go right here. So we're going to take a look at one more example, a little twist on this. This time, the key word here is telling us that we're going to use a linear approximation for f at x equals 7. Whenever we're doing linear approximations, what we want to do is we want to write the equation of the line, and it's going to be a tangent line. So this is going to be y minus blank times x, blank times x minus blank, using point slope form and going back and filling in. We know that x is 7. We now need to know the y value when x is 7, but that's given to us right here. So that's going to be 14. And then we need to know the slope at 7, and that's given to us right here, which is 13/4. So this becomes y is equal to 14 plus 13/4 times x minus 7. We are saying that our line, our tangent line, is going to be very, very, very close to our function as long as the inputs are close to 7. So we're being asked to estimate f of 8. So we can say that f of x is approximately the same as 14 plus 13/4 times x minus 7, as long as x is really close to 7. So using this for f of 8, we're saying that when we plug in 8, we're going to get a very, very, very good approximation. So this is going to be equal to 14 plus 13/4, because 8 minus 7 is 1. 14/4 is 56/4 plus 13/4, which is going to give us 69/4. But again, we could have just left the answer right here on the AP exam. They'd be very happy to accept that. So now the only other question is this an over approximation or an under approximation? Well, this goes back to thinking about increasing, decreasing, concave up, concave down. We were told that our shape was increasing concave down for the function, increasing concave down. If I draw that shape, increasing concave down, and I draw a tangent line anywhere on that, that tangent line is going to be above my shape in every situation. So let's just say that this point right here was our point 714. We're trying to move over one step and get to 8. So there is the point we're actually after. That's 8 comma f of 8. But because they asked us to do the linear approximation, we're actually computing this point right here, which is 869 over 4. So that means we have an over approximation. Now, what makes it an over approximation? Well, it's not that we're increasing or decreasing the function. It's that the function is concave down. So this is an over approximation because f of x is concave down on the interval from 1 to 10, which was given in the beginning of the step, okay? So whenever you're talking about concavity, you always want to see your concave down on an interval, not just at a point. Concavity has to be over an interval. But if you are concave down, your tangent line will always be above it. Likewise, if you are concave up, then your tangent line will always be below it. So for a concave up shape, the tangent line will always be an under approximation. But for a concave up shape, a concave down shape, the tangent line will be an over approximation. So I hope this makes a little bit of sense in terms of Riemann sums and over and under approximations for both Riemann sums and for tangent lines. Hopefully that helps you all, and good luck.